And we're back. So we have this idea of limits at infinity. Remember, there's a difference between the phrase infinite limits and limits at infinity. Infinite limits are ones where the y value of the output is going to infinity. The limits at infinity are the ones where I'm saying x is going to infinity, right? And then see what the output actually is. Remember, limits at infinity tie hand in hand with horizontal asymptotes. Infinite limits were those vertical asymptotes. And that's what we were seeing in this problem here, right? We saw that these vertical asymptotes, man, I got really dotted line happy there. These vertical asymptotes are the ones where as x approaches that number, it goes to infinity. The horizontal asymptotes here and here, that's where as x goes to negative infinity, it levels off on the left side. As x goes to positive infinity, it levels off on the right side. Okay, so that's what we're looking at here. Limits at infinity. So let's take a look here. Let's find the limit as x goes to infinity of 1 over x, and the limit as x goes to negative infinity of 1 over x. Get my notes. Oh, I think they're right here. I was prepared and I didn't remember. All right. When you're calculating the limits at infinity, can you just do direct substitution? I mean, you may be thinking like, okay, well, how do I plug in infinity? Because that's our bread and butter, man. If you can do direct substitution, life is awesome. But how do you really plug in infinity, right? Can you really plug in infinity? I guess that's what we're saying. What does this actually mean, right? What does that actually mean? Can I actually do direct substitution? Well, I guess first off, is it continuous? Is 1 over x continuous around a? Well, a is infinity. Is it continuous all the way to the right side? Well, think about the function 1 over x. Just the plain old function 1 over x, that's our something looking like this, right? Is it continuous as I keep going forever to the right? Yeah, I guess so, right? So if it has continuity, I should be able to plug in. Well, understanding what this means, remember, infinity is not actually a number, it's a concept, right? Infinity is not actually a finite value, it's an idea that it's going to keep getting continually bigger and bigger. So for example, it might be easier to put a stopping point on it and say, okay, what if I just make that number bigger? Like do our old method of plug and chug. Like, okay, so 1 over 100. Pretty small number, right? What if I increase that? 1 over 1,000. What if I increase that? 1 over 10,000. What's happening to that number? What's happening to that number? It's getting smaller and smaller and smaller and closer to what? 0, right? So we can say that the limit as x goes to infinity of 1 over x is 0. Which makes sense because we know what 1 over x should look like. It's got a horizontal asymptote out there. And it's bottom heavy, got a horizontal asymptote at 0. Is that same thing true for the left side? What does this mean? 1 over negative infinity, right? Can I do direct substitution with that too? Well, I guess it's continuous over there, so I should be able to. But does it change anything if I do this? Well, 1 over negative 100? Okay, that's just like a negative really small number, right? What about negative 1,000? What about 1 over negative 10,000? Okay, is it still going to 0? Yeah, it's just going to 0 from the underside, right? From the underneath of it, it's going to 0. It's still going to 0 though, right? The limit as x goes to infinity of 1 over x, negative infinity of 1 over x is still 0. There's no notation where it's like, oh, it's going to 0 from the under. Like this doesn't exist. Like, nah, you don't have to do that. It's just going to 0. It doesn't matter whether it's going from the underside or the overside. Like this was on the top of the horizontal asymptote. This was on the bottom of the horizontal asymptote. There's no notation to tell you that, right? But it's still going to 0. It's still going to 0. So take a look at this. What if we complicate things? What if we say, well, now we've got a polynomial in the numerator and denominator of a rational function? You have to remind yourself, when are horizontal asymptotes going to occur? When could they possibly occur? Well, when we have rational functions, that's one example. When we have exponential functions, that's another example. Okay? Not logarithmic. Logarithmic are vertical asymptotes. But there are times when horizontal asymptotes would occur. If a horizontal asymptote wouldn't occur, well, then you've got your end behavior dance, to fall back on. Or if it's just going to keep getting more positive, well, okay, that's a different animal there. Well, take a look at this. I've got 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Now go with me here. Don't write this down. But I want to explore something. I want to see this. What if I chose to try to do direct substitution? Because we did it in the last problem and it worked, right? Well, what does this mean? What is infinity squared? Infinity, I guess, right? How do you double infinity? A double dog, dare you? Right? So maybe, and what infinity squared would just be infinity. Okay. Well, 3 times infinity, well, I guess it just keeps getting bigger, right? Minus infinity, minus 2. Like, see, that doesn't make sense. We can't really do this. And then, same thing down here. I guess infinity squared just keeps getting bigger. 5 times that just keeps getting bigger. 4 times that just keeps getting bigger. Plus 1. I mean, infinity plus 1. That doesn't make sense to us, right? And then are these going to cancel? Like, what happens there? So doing direct substitution with infinity doesn't really make sense because, again, it's not a finite number. It's an idea. It's a concept. So, but there are ways around that. We were able to evaluate using infinity because this was a function of 1 divided by x, right? So here's what we could do to manipulate it. What I want to do is divide by the highest power in both numerator and denominator. I'm going to say that again. What you want to do is divide by the biggest degree, the highest power, in both numerator and denominator. So in this case, what's my biggest power that I see? X squared. So let's divide everything by x squared. Now, can I do that? Sure. I'm basically going to be multiplying the numerator by 1 over x squared and the denominator by 1 over x squared. And if I multiply the numerator and denominator of a fraction by the same thing, I'm essentially just multiplying by 1. So yes, I can do that. That's mathematically okay. So it's going to be 3x squared over x squared minus x over x squared minus 2 over x. I better write that a little clearer. Minus 2 over x squared, all divided by 5x squared over x squared minus 4x over x squared plus 1 over x squared. This might seem tedious to you, and yes, once you get better at this, you can kind of skip this step because what is going to happen here? Things are going to cancel, right? Things are going to start canceling. So what is this going to equal to? Well, that's just going to be 3. That's going to be 1 over x, right? X over x squared is 1 over x. Well, nothing cancels here. 5x squared over x squared is just 5. 4x over x squared is just 4 over x. And 1 over x squared is just 1 over x squared. Okay, now can I do direct substitution? Now does plugging in infinity actually mean something? Well, let's see. Okay, do I do anything to 3 and 5? No. This would be 1 over infinity minus 2 over infinity squared over 5 minus 4 over infinity plus 1 over infinity squared. Okay, we just took a look at this a second ago. What is 1 over infinity going to go to? 0. So that is going to go to 0. Well, if I square infinity in the denominator, isn't that just going to go to infinity again? What's 2 over infinity? 0. If I keep making the denominator of a fraction even bigger and bigger and bigger, that makes the number smaller and smaller and smaller. This is going to go to 0, and this is going to go to 0. See, I'm kind of canceling them out by saying, well, those are eventually going to be negligible. The bigger I make x, the smaller and smaller and smaller that gets until this converges to what? 3/5. Which, my friends, we should have known. Why should we have known that from the very beginning? What tells us that this should have been 3/5 from the very beginning? From back in Algebra 2. Where's the horizontal asymptote going to be? 3/5. Why? Because I've got equal degrees, right? And equal degrees, we divide the leading coefficients, okay? Guys, this is actually like the calculus proof of why that rule exists. Because if you divide everything by the highest power, if you manipulate it a little bit by dividing by the highest power on x that's there, and then you send it to infinity, it's going to make everything else except for the leading coefficients go away, become more negligible, which means that it's going to converge to the leading coefficients divided, which is 3/5 in this case. Okay. I always find that interesting because like we just learned that rule. It's just like something that you just accept to be true back in Algebra 2, but this is why it's true because we evaluated the limit in that way. Okay. Let's take a look at another one here. Find the horizontal and vertical asymptotes of the graph of the function. I guess the first thing we can do is the vertical asymptote. And I say that singular form. Where is the vertical asymptote here? Or where do I look? What can I do to find it? What do I do? Somebody tell me. Oh, come on. I can't remember. My mind has gone blank. How do I find a vertical asymptote? Oh, no. What do I do? Yeah, set the denominator equal to 0. 3x minus 5 equals 0. X equals 5/3. Okay, there's my vertical asymptote. Okay, now the trickier part of this is the horizontal asymptotes. Right, the horizontal asymptotes. Is there any sort of rule where I can like divide by the highest value? Oh, no, I can't really do that, can I? Because I've got this weird, funky looking square root. Well, what if I tried to? What if I tried to divide by the highest power, right? I would want, in the end, I would want, I'm kind of doing a little side work here, just showing what the end goal is to be. Like I want that to happen, right? I want to divide by the highest power on x. Now, here's the deal. To do that, I'm actually going to be dividing by just x. Let me show you what I mean. Let's divide each piece by just x. 3x over x minus 5 over x, 2x squared plus 1 over x. Okay, now why am I doing just x? Why am I not doing x squared? Because isn't this x outside the house? What would it become if I wanted, and these are going to cancel now, I'll just do the denominator here, 3 over 5 minus x. Okay. What's that going to become if I put it back inside the house? What's an x going to become if I put the square root over top of it? X squared, which is what I wanted, right? 2x squared plus 1 over x squared. See, when you have a square root function like this, you got to kind of be a little tricky with it. Now, what does that mean? Well, I got to do a 2x squared over x squared plus 1 over x squared. Yeah, you can split it up like that. I'm just making the uncommon denominators. Over 3 minus 5x, 3 minus 5 over x. And that will become the square root of 2 plus 1 over x squared all over 3 minus 5 over x. Now, what's going to happen when I go to plug in infinity? Okay, nothing is going to happen at the 2 or the 3, right? And I go to do direct substitution in here, that is going to go to 0. That is going to go to 0. So where is my horizontal asymptote? Radical 2 over 3. There is an explanation on why. It might be a little over your heads right now, but it actually exists at both positive and negative. The short end of it is the fact that when I went underneath the radical, I had to both consider both the positive and the negative version of that root, and that's why the negative is there as well. You could also just look at the graph and see that it's even, and see, oh, look, the horizontal asymptote is going to be the same on the left side. Okay, or just algebraically show that it's even. Let's compute this limit. That's about right. 17. Oh, yeah. 12 minutes. Tomorrow looks like it's going to be a work day. Well, mostly work day. Probably just a couple more slides. Compute the limit as x goes to infinity of radical x squared plus 1 minus x. So we're kind of seeing that fractions are our friends here, right? Fractions with x in the, I know that seems, a lot of you are like, no, they're not. But fractions are our friends when you have x in the denominator, right? Because if you have x in the denominator and you make it go to infinity, it's going to just go away, right? So maybe there's some way that I could compute. Now, can I just do direct? I should have prefaced this by saying, can I just do direct substitution here? Like, infinity squared plus 1, okay. Square root of that, minus infinity. I don't know. That just seems really weird to me. Okay, so no, can't do that. But maybe there's something that we could do with a fraction. Okay, maybe there's something that we could do with a fraction. So what do I mean by that? Well, if I've got this is over 1, right? What's that trick to putting things back down into the denominator? Multiplying by the conjugate, right? So sure, let's try it. Let's see if that helps us. right, let's see what happens. Now, on the top, that's going to be x squared plus 1. Inners and outers, again, are going to cancel. Minus x squared. And then we have this over x squared plus 1. Oops, made that square root way too big. Plus x. Oh, perfect. So 1 over so if I plug in infinity now, what's this going to go to? 0. Yeah. Because is there any part of this like tricky minus sign that's going to catch us up or get us caught up anymore? No. Take a look. If I plug in, it's going to be the square root of infinity squared plus 1 plus infinity. Now, it may be weird to think that I've got to square root infinity. However, square rooting infinity just makes it just a little bit smaller, right? And then I add infinity to it. Is it ever going to get smaller again after I add infinity to it? No. It's just going to keep getting bigger and bigger and bigger and bigger. It's not going to go as fast as it would be if it was just a 1 over x, because I got to square root it first, right? But is it still going to go there? Yeah, eventually, and it's infinity, so eventually, yeah, it happens. So this is going to be, this is end up going to be 1 over infinity, which ends up being 0. Let's stop there for today. Sound good?